talking to us today. Archie did his PhD in Oxford, working with Alex Shekachian and Gianluca Grigori, and now he's a postdoc in astrophysical sciences at Princeton. And he's got interests in turbulence and magnetic fields, particularly in laser plasmas. And he's going to tell us today about turbulent dynamo processes in laser plasmas. So please, Archie.
Great. Well, thank you very much. Let me just share my screen. Can you see that clearly?
Yeah, looks good.
Perfect. Great. Well, thank you very much. So I'd like to start by thanking the festival organizers for giving me the opportunity to speak about this topic. It's a real delight to be here, although perhaps slightly more of a delight in future to actually be in Aix-en-Provence. But yeah, thank you very much for the invitation. Yes, so today I'm going to be talking about investigating turbulent dynamo processes with laser plasma experiments. Now, to start off with, I should also thank all of my collaborators on my project on these experiments, of which there are many. Particular thanks are due to my supervisors, Alex and Gianluca, who've just been mentioned, but also Petra Seferakos, Laura Chen, Jenna Meinecker, Charlotte Palmer, Alexei Kastner and Don Lam, and also my current advisor, Matthew Kuntz. Okay, so I'm going to start off by giving some background and a motivation for the interest in these experiments. And actually, hopefully, there's been already a few talks on dynamo theory in the earlier weeks, so I'm not going to recover a lot of the ground that was particularly covered in Steve Tobias's talk. But essentially, a good place to start is there's this long-standing theory due to Batchelor over 70 years ago, suggesting that non-helical plasma turbulence is capable of amplifying a weak seed magnetic field until it attains a dynamical strength. And this mechanism is known as the fluctuation dynamo, or a small-scale turbulent dynamo. And the reason in astrophysical context this mechanism is of great interest is that it provides a plausible mechanism for explaining the observed dynamically significant fields that are seen in many different astrophysical environments. The fluctuation dynamo is pretty well understood in the framework of magnetohydrodynamics. And in that framework, analytical calculations and simulations, such as that by Alex Shekachian, shown here, give a consistent picture showing that the process is possible, but only if the magnetic Reynolds number, defined here where U is the fluid velocity, L is the outer scale of the turbulence, and E to the resistivity, is bigger than some critical value. What does this look like in an actual periodic box simulation, for example? So again, this is the same simulation that I've just shown here. So if one introduces a weak seed field into this periodic box turbulence, this field is then only subsequently amplified up to such that delta B becomes a finite fraction of U if Rm is bigger than this critical value, which in this case was about 200 for these were low Prandtl number dynamo simulations. Just to note, and I'll come back to this, that one can actually have amplification if one is below this threshold. Kind of characterized as a pre-dynamo regime, but crucially, the degree of amplification is proportional to the magnetic Reynolds number and also dependent on the seed field strength, unlike in the dynamo regime when one is always just amplified up to the dynamical significance. The critical value of the magnetic Reynolds number is thought to be a function, well, it's known to be, I should say, a function of the magnetic Prandtl number, defined as the ratio of the magnetic Reynolds number to the fluid Reynolds number, and is generally believed to be larger for the low Prandtl number regime than the order unity or high Prandtl number regime. The reason for the difference in these two regimes is the physics underpinning these two regimes is very different. In the low Prandtl number regime, the resistive scale on which an initially dynamically insignificant field grows is within the inertial range of the turbulence, and so the velocity field can be characterized in some senses as rough. In a technical sense, I should say. Whereas in the order unity or large Prandtl number regime, the resistive scale is below the Kolmogorov dissipation scale, and thus the velocity field is smooth. And so this changes the fundamental kind of interaction between the velocity field and the magnetic field, hence the difference between the two regimes. MHD compressible dynamo simulations have shown that dynamo action is also possible in compressible turbulence, but in terms of various key measures, it's generally less effective. So, for example, if one transitions from a subsonic into a supersonic flow, as shown here by these federations like Chris Federer, the typical growth rate of the dynamo decreases as the Mach number moves past order unity. In addition, the ratio of the magnetic kinetic energy in the saturated state decreases as one moves into the becomes increasingly compressible. And finally, the typical values at which dynamo action is possible, values of RMC, increase by maybe a factor of 2 to 3 as you move through into the supersonic regime. So that's what is known, thanks to, as I said, analytical calculations and simulations about the fluctuation dynamo. However, I think it's fair to say that there are still some uncertainties. I can't list them all here, but of two questions that are particularly interesting to me are, firstly, the question of how efficiently are scales that initially generated the resistive scale, how efficiently do they then migrate to larger scales? And this migration is arguably essential to explaining the observed observations, the observed scale of the fields. This is seen in, say, the intercluster medium. And there has been some very interesting work on this. One particular set of simulations that I think are amazing are some recent simulations by Lisa Gashnikova and Matthew Kuntz doing very high resolution fluctuation dynamo simulations in the large particle number regime, which do seem to actually show quite efficient migration. Another area that I'm quite interested in is just understanding whether fluctuation dynamo is actually possible in weakly collisional or collisionist plasmas in which the framework of MHD doesn't a priori necessarily follow. Now, again, there have been probably in the last 3 to 5 years started to be simulations of collisionist dynamos and finding that actually the process can be possible, but only under certain conditions. And in addition, there have been some indications that some of the theoretical properties of dynamos can be quite different in these collisionist plasmas. So it remains to be seen, and there's still, I think, quite a lot of work to be done understanding the fluctuation dynamo in plasmas as they actually exist in, say, the intercluster medium. So that's a brief introduction to the kind of the theory underlying the fluctuation dynamo. But I would argue that one of the most interesting developments in the last 20 years in understanding hydrodynamic dynamos more generally was the possibility of conducting experiments in addition to numerical and analytical studies. It obviously goes without saying that it's much, much easier to diagnose a simulation, but I think you'll all agree that it's conceptually reassuring to be able to verify or falsify a dynamo theory in an actual plasma or system. So historically, the first dynamo experiments were performed in liquid metals. The most famous of these was the Riga dynamo experiments. There's a very nice review a few years ago about this, where the vessel, the Riga dynamo, is shown here on the top right, and basically a helical liquid sodium flow was found to produce the first kinematic dynamo, and then subsequently a dynamically significant field a few years later. This year you have helical flow going down and then a backflow in the pink regions here, and the resulting field is shown on the top right here. And there have been the various subsequent experiments in liquid metals that have all produced self-excited eigenmodes at sufficiently large magnetic Reynolds numbers. Particularly interesting one is that due to Monchot, where in addition to a kind of a mean helical flow, there was strong evidence of turbulent motions as well, and there was dynamo action was seen at RM of about 40 or larger, in that 30 to 40 or larger, depending on details of the exact flow. So just before moving on to that, I think we've already learned in these last 20 years quite a lot about hydrodynamic dynamos, particularly ones with helical flows. And moving forward, liquid metals will continue to be an important tool in exploring properties of dynamos. However, liquid metal experiments are always limited to particular regimes. They are always in the very low Prandtl number regime. It's very hard to get magnetic Reynolds numbers in these experiments larger than kind of a few hundred or perhaps 1,000, even the most recent setups. And typically the fluid Reynolds numbers are greater than 10 to the 6, or sometimes even much larger than that. These flows are always highly incompressible. And in addition, obviously, given their liquid metals, one is unable to explore the effects of plasma microphysics and dynamos, the sort of effects I discussed briefly in the previous slide. And so therefore, if we wish to kind of move beyond these particular regimes, which we certainly do if we wish to understand dynamo processes in, say, the intercluster medium, where the magnetic Prandtl number is large, flows can be compressible and plasma microphysics is thought to matter, we need alternative experimental approaches. And I'm going to talk about a possible new experimental approach that could help to fill that gap today, and those are laser plasma dynamo experiments. The approach here is conceptually quite simple. We simply create a turbulent blob of plasma by colliding laser-driven plasma jets. The first such experiment of this form was carried out on the Vulcan laser at the Central Laser Facility in the UK, with the main experiment, the experimental lead being Jenna Meinecker. And so this shows the idea here. So in her experiment, two carbon rods were irradiated with 300 joules of laser energy each. This created jets from the far side of these two rods, and then these jets subsequently collided. Okay, I'll keep going. So in addition, in further induced turbulence in some of these experiments, a grid was used, and I'll come back to the role of grids in inducing turbulence in these systems. But just to illustrate an idea, this is an optical image from one of her experiments, and one can just about make out something that looks like a turbulent plasma upon the collision of these two jets. So this very initial experiment, and I should say various plasma diagnostics were employed to characterize the state. I'll come back to plasma diagnostics and give a bit of a one-on-one on those subsequently. But just to briefly outline the findings of these, we found, well, in these experiments, an initial field strength was amplification of around a factor of 2 or 3 was found, and the plasma, having been characterized, was found to have a magnetic Reynolds number of quite small, of about 5, very low Prandtl numbers, and subsonic Mach numbers. So therefore, the conclusions from these experiments, whilst there was some evidence of magnetic field amplification, if one really wanted to access the true dynamo regime, one would need to go to obtain a much larger magnetic Reynolds number. And to do this, one needs to go to the highest energy laser facilities that currently exist, specifically the Omega Laser Facility, the Laser Megajoule in Bordeaux, or the National Mission Facility in Livermore. So that's what was done, and the subsequent recent experiments investigating laser plasma dynamos have yielded what I think can be now described as quite a significant collection of results. Probably the most famous of these results, which was published 3 years ago now, was the first demonstration of fluctuation dynamo action in a low Prandtl number plasma. More recently, we reported time-resolved measurements of demonstrating fluctuation dynamo action in a plasma with order unity or larger magnetic Prandtl numbers. We've also demonstrated the pre-dynamo amplification magnetic fields by supersonic plasma turbulence, a platform that was developed from the first ever realization of boundary-free supersonic turbulence in the laboratory due to Tom White. And then another experiment, which is only partially out in the public domain so far, but is very intriguing results, a potential demonstration of fluctuation dynamo action in a plasma with very large magnetic Prandtl number. And then finally, some results demonstrating, actually following on some feedback from our first experiments, demonstrating that the post-amplification strength of the magnetic fields arising in these experiments is set by the turbulent dynamics, not the seed field strength. In addition to these kind of very dynamo-focused experiments, we've actually used this experimental platform already for a few other applications. I'm probably not going to have time, I think, to talk about these today, although if there is time at the end, I'd particularly maybe like to mention this second result here. But yeah, the 2 applications so far was a measurement of the transport of high energy charged particles through some intermittent magnetic fields. And in addition, an observation of suppression of heat conduction in a turbulent magnetized plasma, both of which are quite kind of not necessarily applications we considered early on, but having developed the platform, it seemed apt to then explore these possibilities. So what I'm going to do now is I'm going to discuss these experiments. But first, I thought it would be helpful, given I'm not sure how familiar everyone here is in kind of the sort of diagnostics that are used on these high energy laser facilities, I thought I'd give a brief 101 on the 3 main diagnostics I'm going to discuss today. So the first of these is X-ray imaging, which is probably the kind of simplest conceptually. So the experimental data, 2 examples of which I'm showing here, are for this diagnostics are simply just images of soft X-ray radiation emitted by the turbulent plasma. For some of our experiments where we're using just a CH plasma, this radiation is dominated by Bremsstrahlung. In other of these experiments, dopants were used, and then in those cases, the line emission can be significant. Another thing about understanding these images is that the plasma is optically thin to soft X-rays, so the measured intensity is capturing emission along the entire line of sight in these images. The X-ray emission is detected using a framing pinhole camera, which is configured with a microchannel plate and a filter to remove anything but the soft and frankly also hard X-rays. But the emission is seen as then dominated by the soft X-rays in this case. The microchannel plate works in the following way: the X-rays hit it, and that releases electrons, and those electrons then hit a phosphor-plate. This creates photons, and then those photons are detected by a charge-coupled device camera, and then you end up with the image like this. The whole setup is calibrated so we can kind of back out for one of these images X-ray intensity, or measured X-ray intensity. Furthermore, the microchannel plate is only operated at the pre-specified time over quite a short time gate, so we can basically specify in advance when doing the experiment when we want to kind of obtain the image, and then often, depending on the facility, we can often obtain multiple images on the same shot, but then we can also do repeats and obtain images at different times depending on what processes we're trying to explore. Finally, what information are we gaining from these images? Well, the main thing we use this is twofold. Firstly, the collision dynamics, working out when the jets collide and the subsequent formation of the interaction region plasma. And then in addition, we use this diagnostic to characterize the plasma turbulence, and I'll come back to exactly how we do that subsequently. So that's the first diagnostic that we use a lot. A second diagnostic is Thomson scattering. So what this diagnostic is measuring is this a spectrum of collectively scattered Thomson scattered laser light of a probe beam. Now, in this regime in which the Thomson scattering is operating, given the wavelength of the laser probe beam, one detects two specific features associated with plasma waves just inherent in the plasma: the ion acoustic wave spectrum, which is shown on the top left here, and the electron plasma wave shown on the bottom left here. And as you can see, these are different characteristic wavelengths. Depending on the experiment, this can either be configured to give a time-resolved measurement in a 50 micron cubed volume, which and compared to the whole size of the interaction region of these interacting plasmas, this kind of millimeter scale, this is effectively a point measurement. Or alternatively, we can do a spatially resolved measurement in a kind of cylindrical region, and then that allows us to get a better sense of average quantities. Although if you do a spatially resolved measurement, one has to then integrate over a certain time period of about a nanosecond in these experiments. And just for reference here, this data I'm showing here is from spatially resolved data, which we then average to give average values for in this plasma. So the scattered laser light is measured. The signal is split using a beam splitter, and then two different spectrometers measure both the ion acoustic wave and electron plasma wave feature respectively. And then the information we're gaining from this is effectively key macroscopic plasma parameters. So more specifically, the ion acoustic wave feature here, the electron temperature is given by the width between these two peaks. The effective ion temperature, which is composed of the actual ion temperature as well as any turbulent motions, is given by the width of the peaks. Sorry, I should say the electron temperature is the distance between these two peaks. The effective ion temperature is the width, and the bulk flow velocity is given by the shift of these two peaks with respect to the kind of the initial frequency of the incident frequency of the laser probe beam, which is this shown by this line here. For the electron plasma wave feature, the mean position of the peak allows for to measure the mean electron number density, and then in addition the width of the peak allows for spread in densities, and then making a kind of reasonable hypothesis relating the spread in densities to the turbulence velocity, and in particular the turbulent Mach number. This basically allows us in principle to decompose the effective ion temperature into a turbulence and the actual ion temperature components. So we can effectively back out the electron ion temperature densities and characteristic flow velocities from this diagnostic when we're using both of these features. The final diagnostic we use on basing all of these experiments, proton radiography. What is measured here are inhomogeneous distributions of proton flux, where effectively we've generated a proton beam with several MeV energies, which has an initially smooth profile, and we generate these either using a very high intensity laser source, such as that shown here, the Patel laser in Bordeaux. This was the experiment done at the Laser Megajoule facility. Or using a D3 helium fusion capsule source, so using fusion photons of 3 MeV and 14.7 MeV respectively. And effectively, this proton beam is generated. It has very short pulse duration compared to the characteristic plasma evolution times, and this pulse just passes out from the source direction, passes through the plasma of interest, and is then subsequently detected. The detection is either, depending on whether one is using a laser-induced proton beam or a fusion proton beam, depends on how this is typically detected. For the laser proton sources, proton beams, a calibrated radiochromic film stack is typically used. Alternatively, yeah, for the D3 fusion capsule source, a solid state nuclear track detector, CR39, is used, and then proton bins, individual proton pits are actually counted using an automated scanning device. And just to give you a sense, so as I said, this experiment here was using a laser source, and so these are from us. These are detected from RCS stacks, and these are basically 3 sample proton radiographs that we obtained, and you can see structures associated with the interaction region plasma. The information that we're gaining from this, and I should say why we're doing this in the first place, is that it's effectively to gain measurements of the magnetic fields prior to and post amplification. The low number density of these beam protons compared to the number density of the inherent plasma means that these the protons can basically be regarded as non-perturbative tracer particles. And in addition, the high speed of the proton beam relative to plasma's evolution means that the deflections are pretty small and are dominated by Lorentz forces due to the magnetic fields already just sitting in the plasma. And so effectively, if you have inhomogeneous magnetic fields, this causes inhomogeneous deflections, and then this shows up as inhomogeneous structure in the image. And it turns out that provided the deflections aren't so large as to cause the proton beam to self-intersect itself prior to reaching the detector, there's actually a unique relation between these inhomogeneities and the 2 components of the path integrated magnetic field, specifically the 2 components of the magnetic field that are perpendicular to the kind of predominant transit direction of the proton beam. And so from this, one can basically back out information, one of these images, information about the path integrated magnetic fields, and then under further assumptions, then obtain direct measurements of, well, then obtain measurements of, inferred measurements, I should say, of the magnetic fields. So that's a brief one-on-one of all the plasma diagnostics we're using on these experiments. I thought we also, in addition to collecting experimental data with these diagnostics, we run fluid laser plasma simulations of the experiments. These were all carried out by Petros Safarakos at the University of Rochester using a flash code, which is a 3-temperature radiation non-ideal MHD code with laser, including laser deposition and physical resistivities. So this is a simulation of actually our most recent published work, showing on omega, showing the density at the point at which these jets are about to collide. And then this is 6 nanoseconds later, showing the formation of this interaction region plasma, region of higher density, and also higher temperatures and magnetic fields, and then the subsequent expansion of this interaction region plasma so it obtains a larger volume. And generally, the simulations are helpful for a number of 3 reasons. The first of these is helping with the experimental design, and then also planning when to apply our diagnostics. As I said, we have to specify in advance before carrying out the experiments. And typically on these very high energy laser facilities, one doesn't get a huge number of experimental shots. And so you have to really plan carefully to maximize the quality of the data you're obtaining. They're also very useful for aiding the interpretation of the results. Apart from anything else, we can directly calculate physical quantities in 3D in these simulations, whereas we only have these indirect diagnostic techniques for measuring things as they were actually realized in the experiment. Flash is also configured to be able to simulate diagnostics, the 3 I've mentioned. And this is very helpful because we can then directly compare the outputs of the diagnostic between the simulation and the experiments, and then see to what extent the simulation is accurately modeling what is going on in the experiments. Finally, on particularly a point that's particularly relevant to Dynamo, and we'll see this coming in a few different contexts later on, these simulations provide a really important bridge between periodic box simulations of the fluctuation dynamo and the actual experiments. It turns out that given the way that these turbulent plasmas are formed, there are important kind of geometrical considerations, for example, that mean that certain effects show up in the experiments that are not going to appear in a periodic box simulation of a dynamo. And so these flash simulations provide a bridge between those 2. Okay, so I think I've now introduced you to the simulations we've done and also the diagnostics. It's now time to talk about some of the results of these experiments. So I'm going to start off by discussing this first demonstration of fluctuation dynamo action in a low Prandtl number plasma. So this was the first experiment chronologically to exhibit fluctuation dynamo action, and this schematic here shows the experiment. So in this case, which was carried out in the Omega laser facility, we had two plastic foils with a 6% chlorine dopant in this case, that were irradiated with 5 kilojoules of laser energy each. We tried actually at this point various different pulse lengths, but I'm going to focus on the 5 nanosecond pulse length results. In this case, this irradiation of these two plastic foils creates rear side blow-off plasma jets. These jets are then, on this Omega experiment, will then pass through 2 grids. And as I mentioned briefly before, the grids help induce turbulence, a bit like water flowing through a grid in the jets. But it turns out the main function of these grids in really efficiently generating turbulence in an interaction region plasma upon their subsequent collision actually comes from introducing misaligned grids. So what do I mean by that? Well, grids where there's a hole on one side, there's a rod on the other. And if one uses grids like this, when the jets then subsequently collide, one ends up with very strong shearing flows in the kind of interaction medium plasma that forms, and then these shearing flows rapidly become unstable. So I think the Kelvin-Helmholtz instability, and one quickly ends up with something that seems to look very turbulent in a remarkably short period of time. So having created this turbulent plasma in this way, this was then probed using Thomson scattering, as I mentioned, X-ray imaging, and in this case, a D3 helium capsule to perform proton radiography with this geometry here, so kind of coming through the region at an angle. Starting off with reviewing the results of the Thomson scattering diagnostic, with this successfully ascertained the plasma parameters in the experiment. So we're talking the turbulent velocities attained in this plasma about 100 kilometers a second, characteristic temperatures about 400 eV, and number densities of 10 to the 20 inverse cubic centimeters. And then putting this into kind of fluctuation dynamo relevant parameters, assuming this plasma, and I'll come back to this assumption, is a 2 ion species collisional plasma, and one can infer the fluid and magnetic Reynolds numbers and the Prandtl number. And so one finds in this first experiment, typically the fluid Reynolds numbers were the order of 1,500 to probably 2,000, magnetic Reynolds numbers of about 500, and Prandtl numbers of about 0.3. I should point out that, and I'll come back to this probably should be thought of as an upper bound for this experiment in terms of the values obtained of this magnetic Prandtl number. So that evidence shows that we have managed to form a plasma, but it's in the low Prandtl number regime. We've characterized the development of the turbulence, as I mentioned, using this X-ray framing camera, and in particular, making the assumption that this plasma is optically thin and the motions are subsonic. And these assumptions are both well justified for this case. And I can discuss how we justify those if people here are interested. We can then relate the relative emission intensity fluctuations to relative density fluctuations in the plasma, borrowing a technique that's actually used quite common in observational astronomy. And then, given the plasma motions, turbulent motions are subsonic, we can regard the density as being a passive scalar, and thus the power spectrum of the density is the same as the power spectrum of the turbulence. And so here's one of our images here, and we can, using techniques, basically back out a spectrum of the fluctuations here, and we find structures and range of scales and a spectrum that's consistent with Kolmogorov turbulence. So the conclusion from this is the interaction region does seem to be manifesting turbulence, and even if we're being a bit more conservative, it's certainly manifesting stochastic motion, if not necessarily a fully developed turbulent cascade. Now moving on to the magnetic field measurements, which, as I said, we're done with proton radiography. So the image I'm showing you at the top here, which was 29 seconds after the driving laser pulse, this shows very little structure, and these images are at the point of collision. So in effect, if we see very little structure, that shows that there aren't fields, the sort of inhomogeneous fields that's causing significant deflections. However, if we move 5 nanoseconds later, you can see that there are all these very significant structures emerging in these images. As I mentioned, we can take these images and back out path integrated perpendicular magnetic fields, perpendicular with respect to the direction of the probe beam. And one sees that there's a clear change in these path integrated fields from the kind of at pre and at collision structure of the fields compared to the post collision structure, both in terms of their strength and their morphology. Because this was the first time we fielded this a process of going from the path from the field, the image itself to these path integrated fields, we also employed another standard laser plasma diagnostic polarimetry, looking at the rotation of the polarization of the Thomson scattering probe beam to confirm any magnetic field measurements we obtained. And the good news is that we found consistent values from both the proton radiography and the polarimetry. And we obtained strong magnetic fields of the order of 120 kilogauss and an associated energy amplification from pre to post collision of about 600 times. And the resulting magnetic energy of this 120 kilogauss field is comparable, was comparable to the kinetic energy of the turbulent motions at the driving scale, around 4%. And so this was both the evidence of significant amplification and a finite value of this energy ratio gave cause to believe that a fluctuation dynamo is operating in this case. So that was the first experiment. And a second experiment was looking at time provided, as I said, this time result demonstration of dynamo action in an order unity magnetic Prandtl number. So how did we access this different plasma regime? Well, we learned lessons from the previous experiments to and also run extensive numbers of design clash simulations to kind of optimize the parameters on the same facility. In particular, we found the most significant factor was if we removed the chlorine dopants from the foils, this allowed us to significantly increase the peak values of the magnetic Prandtl number. We also made a number of platform improvements. We introduced this kind of can design instead of the rods that we had before. This increased the field of view. We changed the grid design and increased the open fraction of the holes compared to the size of the rods, because the simulations indicated this would improve the homogeneity of the interaction region, and thankfully it turned out the simulations were correct in this regard. And finally, thanks to the kind of the experience gained from the previous experiment, we had a very good idea of when the collision occurs, and this allowed us to really maximize the quality of the data we were collecting and thereby obtain time-resolved measurements of the evolution of various different plasma properties. And again, we fielded the same diagnostics that we used before, although for this experiment, we also included the electron plasma wave feature. I should have said on the previous experiment, we only had the ion acoustic wave feature. And it's the reason for this that one either has to use polarimetry or measure this feature. And so having confirmed that our proton radiography measurements with the magnetic fields were accurate, we could drop the polarimetry and instead use measure the actual electron plasma wave feature. So I'm going to start off with the time resolved measurements showing you the X-ray images. So again, just a reminder, this is looking at self-emitted X-rays, and the resolution in this case was 50 microns. And so this initial time sequence of first 4 images is going to illustrate the formation of the interaction region. So this is 23 nanoseconds after the introduction of the laser drive in this case. And one can just about make out evidence of a jet extending from the grid in this case, although due to the low levels of emission, you can see the signal to noise ratio is very poor at this point. At 24 nanoseconds, 0.5 nanoseconds, nothing is detected. However, by 26 nanoseconds, one begins to see evidence of a glowing region of plasma. And then subsequently, the emission dramatically increases due to the higher density specifically, but also the higher temperatures upon the formation of the interaction region plasma. Now looking at the same images, but from slightly more zoomed out, we can take subsequent images to look at the development of stochastic motion in an interaction region. Now, the way this manifests in these images is specifically the emergence of fluctuations in the random fluctuations in the emissivity. So we can see that some evidence of those fluctuations emerges 1.5 nanoseconds later and persists at all subsequent times at which we attained measurements. So the X-ray diagnostic seem to find good evidence that we are indeed attaining turbulent motions in this case. I'm not going to explicitly go through them here, but the time-resolved Thomson scattering measurements we did in this experiment showed us attain, again, temperatures, flow velocities, and the like, and then allow us to infer, again, the key MHD relevant, fluctuation dynamo relevant parameters. And what we found is that during the initial amplification phase of the magnetic field, in principle, at the times at which dynamo should be operating, this first 4 nanoseconds, the magnetic Prandtl number in this case was order unity. The late time behavior was quite subtle. I can discuss that if interested, but effectively, the Prandtl number we're confident the Prandtl number is order unity for this initial period. Furthermore, the turbulent magnetic Reynolds number in this case of about 450 is again above the critical value for fluctuation dynamos operating periodic box MHD simulations of order unity magnetic Prandtl number dynamos. So that's we've realized this plasma that's in this state. Now let's look at the Persian radiography to get a sense of how the magnetic fields evolve. Again, these are time resolved measurements. So we find that these early time images before and around the jet collision have very small amplitude and homogeneities. Again, there's basically nothing in this image. This image here, which is just after the collision, does have some evidence of structure, but it's very weak. And the associated path integrated magnetic fields magnitudes are also very small. However, from about 2 nanoseconds after the collision, we suddenly see these large amplitude flux inhomogeneities appear and associated much stronger path integrated magnetic fields with very different morphology. And these structures persist at all subsequent times. Indeed, the path integrated magnetic field strength obtains monotonically increased for a 10 nanosecond interval, as I'm about to show here. So those are the measurements, the path integrated magnetic field measurements in the Posen images. Now we'd like to go one step further and actually try to back out some information about the magnetic field itself rather than the path integrated field. We can do this very naively by just assuming that the field doesn't have any cancellation along the path. So at the collision, there are 2 ways we do this. We have to do a different technique at the collision when the fields are non-stochastic versus after the collision when the fields have been amplified when they are stochastic. So for the fields at collision, if we assume that we have no cancellation and we assume that the fields are contained in a region of particular length, we can move from a path integrated field measurement to an inferred magnetic field strength, which comes out to about 5 kilogauss. We can be a bit more kind of comprehensive in this and follow a standard technique used to analyze these images when you have regular structures, basically a parameterized path integrated field model, which is obtained from an actual 3-dimensional magnetic field model. And the model that we used was that, on account of it being the most plausible candidate, was effectively 2 magnetic cocoon-like structures. These are azimuthal fields, which are generated by the Bimmer battery mechanism at the laser spots, and then subsequently advected into the interaction region plasma. And it turns out that this part of the integrated magnetic field structure that we see here, and these lineouts of the same structure, is consistent with this sort of structure with an angle, proton beam imaging at the angle that we actually obtained. And so having obtained this 3-dimensional model for the magnetic field structure, we can then evaluate the mean characteristic field strength and do indeed find a value that's actually pretty consistent with this, about 6 kilogauss actually in this case. For the stochastic field structures at later times with these different path integrated field maps, we can make an assumption of isotropic magnetic field statistics, and then with this assumption, we can then estimate the root mean square magnetic field strength, provided the path length of the protons through the plasma is known. And we infer this using the width of the interaction region measured from the X-rays under the assumption that all the magnetic fields are concentrated in the region of high emission, which corresponds to the region of high density. And what we find is the root mean square magnetic field jumps very significantly in a 1.5 nanosecond interval subsequent to collision, reaching about 120 kilogauss again. And this corresponds to about a 24 times application in the field strengths. In addition to the obtaining the root mean square magnetic fields, so the experimental measurements, to be clear, are the red error bar points here. We can also use similar techniques to estimate both the correlation length of the fields and bounds in magnetic field strength. The correlation length here is experimental data shown in blue, and the bounds are shown here in maroon. We can also compare the lines, I should say, are the flash simulated results. And we find quite interestingly, and I'll come back to this, that the root mean square value and the maximum value seem pretty similar, but you'll notice there seems to be quite a discrepancy in the correlation length. And this is one of probably the most interesting findings from these experiments. But back to the kind of key results. So what we're seeing is that there's this growth in magnetic energy, in this case of nearly 3 orders of magnitude from the pre-collision value. And the root mean square of the magnetic energy is again a finite fraction of the kinetic energy, around 3% in this time, with the peak magnetic energies being comparable. And so this led us to conclude that we have indeed created a dynamo that certainly during the amplification phase is in the order unity magnetic Prandtl number regime. And so given this is the first time this has been realized, this was quite an exciting result for us. In addition to that kind of headline result, we can also dig into the data and also the flash simulations of this experiment to learn a bit more about dynamo processes in these cases. And one interesting result that we found was that the inferred exponential growth rate of the field is actually very large, 6 times the outer scale turbulent turnover rate. We found similar growth rates in flash, but this was quite a puzzling result to us initially because periodic box simulations of the fluctuation dynamo with order unity magnetic Prandtl numbers and similar magnetic Reynolds numbers had a growth rate that's only about 20% of this measured rate. And so we had to work quite hard to understand why this growth rate was so large. And we believe the most plausible explanation for this is the presence of strong shear flows in the interaction region plasma, which are directed parallel to the line of centers, that is the line that parallels the initial flow directions, in addition to the stochastic motions. So to illustrate this, I'm showing here the flash simulation. So this is the components of the velocity field and the flash simulations out of the plane. And so this direction from the Z direction is the direction of the initial flows, and then the interaction region is perpendicular. The plane of the interaction region is perpendicular to that. And so, the top row is the outer plane velocity component. The bottom plane is these components to flow velocity in the Z direction. And one can see that there are these shear flows in this interaction region plasma, which have a much larger magnitude than the outer plane velocity components. And so certainly at this initial time when the interaction region is forming, and then actually for a period up until about 31 nanoseconds, one shouldn't actually think of these turbulent motions as being isotropic. And there do seem to be these strong shear flows present. If one in the flash simulation calculates the rate of strain of the simulated velocity field, we then found kind of quite a relief in that this is actually comparable to the growth rate of the field. And so we think basically what's going on here is that these flows are not present in the periodic box simulations, and they seem to really help the growth of the fields in the experimental geometry. Another interesting finding concerns, as I mentioned, the characteristic scale of the magnetic fields. So we found generally that the flash simulations seem to model the evolution of the hydrodynamics and the magnetic field strength with pretty high fidelity. But the characteristic value of the correlation length, or equivalently the integral scale obtained in the flash simulations of the experiment, was much closer to previous periodic box simulations than to the experimental value. So to illustrate this, I'm showing here the experimental data at 2 different times, these path integrated magnetic field maps. And on the bottom here, what I've done is these were simulated, I created simulated flash photon radiographs, and then applied this exactly the same data analysis technique that was applied to experimental data to those simulated radiographs. And one can see qualitatively that the field structures seem to be much smaller by eye in the flash data than they are in the experimental data. A bit more quantitatively, one can then infer magnetic energy spectra from both the experimental data and the flash data. And one sees that the spectra of these two quantities, particularly at early times, seems to be rather different, with more large-scale structures in the experimental data than in the flash data. We, at one point, were concerned that this might just be something to do with our approach for analyzing these photon radiographs. But if one just looks at the simulated radiographs to which the analysis of the flash data I just showed you was applied, one again can see qualitatively that there does the field morphology in the flash simulations does seem to be quite different to that obtained in experimental data in this case. So this was quite a puzzling results for us, and to be honest, we haven't entirely worked out exactly what the cause of this discrepancy is. We think there are 3 viable explanations. The first is that there could be additional physics. This is not present in these resistive MHD flash simulations. An example of this is that once the initial amplification occurs, in this case, which is by 27.2 nanoseconds, these fields are sufficiently strong to lead to an order unity or Hall parameter. That is the ratio of the electron mean free path to the electron gyro radius. And so in principle, one might need to employ an extended MHD model in order to capture the magnetic field dynamics accurately. Another possibility is the observed difference that we actually see also in the spectrum of the initial magnetic fields. There was a recent paper by Setter and Chris Federath, Ahmed Setter and Chris Federath, showing that although it was the case if you have amplification over many orders of magnitude, that the initial spectrum of the fields doesn't matter. For the sort of degree of amplification that we're seeing in these experiments, the initial spectrum of fields does make a difference to the spectrum fields post-amplification. And what we found is the flash simulation, digging into the flash simulations, the field structures in those simulations just after the collision typically at a much smaller scale than those we saw in the experiments, suggesting there could be a difference in the initial field structures. And finally, these flash simulations don't have explicit resistivity, explicit viscosity, although they do have explicit resistivity. And the inferred magnetic fluid Reynolds number in these simulations, because of the changes in the inferred viscosity in the experiments, is actually thought to change quite a lot because the ion temperature is changing rapidly, which affects the viscosity, and none of this effect is captured in the flash simulation. So it is possible that this difference in dissipation mechanisms could lead to different magnetic field dynamics. Needless to say, we found this quite an intriguing result given the long-standing problem of explaining the observed scale of magnetic fields present in the ICM. More specifically, it seems that current ICM simulations, actually the characteristic scale of the fields can often end up being resolution dependent. And so working out how, as I mentioned at the beginning of the talk, how those fields transit from small scales to large scales is an outstanding research problem. And it's just quite interesting that the scale of the fields observed experimentally in this case were larger than in the flash simulation, MHD flash simulations of the same situation. Okay, so those are the first two omega experiments done looking at fluctuation dynamo action in both the low Prandtl number regime and high order unity Prandtl number regime. And now I'm going to change tack a little bit and talk about a demonstration of pre-dynamo amplification of fields by supersonic plasma turbulence. So this is a experiment that was carried out on the laser megajoule and Petal with access to Petal laser, and it's a very similar experiment to the omega case, except we used an aluminium foil, a thinner target, and increased laser energy. And these factors together where flash simulations indicated, should increase the jet velocity and increase the turbulent velocity, but decrease the characteristic temperatures due to increased radiative cooling. And this is indeed what we found. We found characteristic turbulent velocities around 190 kilometers per second in this case, compared to 100 in the previous experiments. Electron temperatures were about a factor of 4 times smaller than the previous experiments, and similar in electron number densities. And again, we can infer turbulent magnetic Reynolds numbers, magnetic Prandtl numbers, and a turbulent Mach number. And we find that in this case, we don't get to as high magnetic Reynolds numbers of around 45 in this case, but still much larger than order unity when back in the low Prandtl number regime. But crucially for this application here, the turbulent Mach number was about 2.3, so larger than order unity. As I mentioned earlier on, we use the Petal laser beam to get proton images at different times in this experiment. And what we can do is take these images and apply exactly the same procedure before back out the path integrated magnetic fields. We also developed a technique to basically separate the large scale fields that are present in the interaction region plasma that are associated with the Biermann fields from the small scale stochastic fields. And the large scale fields are shown at the left here at 2 different times, at 19.7 and 22.7 nanoseconds. And the small scale fields shown on the so it's the left, and on the right here, these are the small scale stochastic fields. And from this, we can look at the evolution, yes, of both the Biermann C fields, and then the root mean square of the stochastic fields. And what we find is that there is amplification of these weak C fields. This is comparable, and these observations and the evolution of the large and small scale fields is pretty comparable to what we had for subsonic turbulent plasmas at a magnetic Reynolds number nearly an order of magnitude smaller to this. It's about a factor of 5. Furthermore, the energy ratio in these cases was very small, about 0.1%. So what we concluded from this is that these experiments had not accessed the dynamo regime, although they had observed a small amount of dynamo amplification. And so this is not a turbulent dynamo yet, although we are trying to work on this and see if we can create a supersonic turbulent dynamo. So watch this space. But in terms of the physics that one can learn from this, this is quite an interesting, the fact that the amplification seems to be less efficient in the supersonic as opposed to subsonic case due to the same amplification occurring at the same, at a much larger magnetic Reynolds number in the supersonic as opposed to subsonic case, is actually consistent with theoretical expectations that I outlined at the beginning, that supersonic turbulence provides a less effective dynamo than subsonic turbulence. Moving on to this kind of more recent results again, we think we have evidence of demonstration of dynamo action in a very large magnetic a plasma with a very large magnetic Prandtl number, although there's a question mark here, which is an important caveat. So I should credit this, the experimental lead again was this Regina Meinecker. So this experiment was carried out in the largest laser in the world, the National Ignition Facility. This is very similar to the Omega laser. The platform used, I should say, is very similar to the Omega laser facility, except using 25 times the laser energy. So you can see here, same target, foils are radiated, plastic foils, and then two plasma jets are created, and then a turbulent region of plasma is created, having those jets pass through grids. And then we probe again using Thomson scattering, using a proton capsule and X-ray imaging. So this is one of the X-ray images obtained from this experiment. We again see fluctuations in the emissivity, and we can relate these to, again, back out a power spectrum in the same way that we did before. And this does seem to suggest that we are again obtaining stochastic motions again realized on this National Ignition Facility experiment. The optical Thomson scattering diagnostics picked up electron and ion temperatures of around 1 keV, densities that are nearly 5 to 10 times higher than the previous Omega experiments, about 8 times 10 to 20 inverse cubic centimeters, and turbulent velocities that are about twice as large, 200 kilometers a second. And then again, inferring the relevant MHD parameters here, this corresponds to magnetic Reynolds numbers of nearly 2,000 to 6,000, and a magnetic Prandtl number of 3 to 50, again, assuming collisional dynamics, which is actually might turn out to be a poor assumption. But this seemed very promising, that we're now in this high Prandtl number regime and very large, much larger magnetic Reynolds numbers than we had before. We then measured magnetic fields again using proton radiography. The initial BIM and seed fields generated laser spots are considerably larger in the NIF case than the Omega case. We already have 60 kilogauss fields. And then it turns out the amplified fields became so strong, almost a megagauss, with maximum fields significantly over a megagauss in this turbulent plasma. The previously established techniques about relating these images to the path integrated magnetic fields completely fail. And so we have to do something much more rudimentary. Instead, we use this pinhole slit, where we basically cut off the magnetic flux, the proton flux prior to the protons passing through the plasma. And so the only protons we should in principle detect will have passed through this slit. And so if there were no fields, all the protons would just sit inside this region here. However, as you can see from the actual data, the protons are scattered all over the place. And this is consistent with there being very strong magnetic fields present in this turbulent plasma. So to be a bit more quantitative, we look at the degree from which protons are spread in 5 different regions along the slit. And then using a technique that we validated with the flash simulations of the NIF experiment, we can then try to back out the root mean square magnetic field and the maximum field from the root mean square and maximum displacements of these deflected protons in these directions. And what we find when we do this process is that the amplified fields are dynamically significant, with the largest obtained energy ratios we've ever seen in these sort of experiments of around 9%. So in short, the dynamo seems to be operating, but one question we have, kind of an ongoing discussion we have, is can we really describe this plasma as being having a large magnetic Prandtl number and also being an MHD dynamo? The reason for this concern is that if one looks at some of the microphysics, for example, and characterizes thermal electrons, even pre-amplification, the electrons are almost approaching being magnetized with their mean free pass over gyro radii, or being order 1. And then post-amplification, this same parameter becomes very large, about anywhere between 8 and 30. If we also look at the hydrogen ions in this plasma, again, initially the field, these tend to be much less magnetized than the electrons for a fixed field strength in these sort of experiments, but so initially they are unmagnetized. But post-amplification, the ratio of this parameter approaches an order unity value. And the reason this is very important is that it turns out that it's not thermal hydrogen ions, but superthermal hydrogen ions that dictate momentum transport and viscous transport in these plasmas. And this for those ions, or those particular hydrogen ions, this parameter is actually becomes larger than order unity, and so we could be beginning to see the effect of the magnetic field on momentum transport in these cases. So although in short, in this experiment, we do see very significant amplification of magnetic fields up to very large energy ratios, it's not entirely clear whether the MHD large Prandtl number framework is the correct one to view this. But irrespective of this, the considerations I made about talking about whether plasma effects and microphysics can affect the dynamo, it does seem quite positive from our experiment that in spite of being in this regime where these effects might start to manage, we are still seeing efficient amplification of magnetic fields. So finally on the dynamo side is this this demonstration of the post-amplification strength of magnetic fields due to the dynamo action is set by turbulent dynamics, not the seed field strength. The motivation for this actually came from feedback from others who were other dynamo theorists and people in the laser plasma community, which the observation that the ratio of magnetic to turbulent kinetic energies we were seeing is still quite small post-amplification. I mentioned 3 to 4%. And so the question that was asked quite frequently is, are the amplified fields actually dynamically significant at these small values, or seemingly quite small values? Then we had the idea, having had been asked this question, that if they weren't dynamically significant, then in principle, if we introduced a larger seed field, this would result in a much larger amplified field. And so we then adapted the platform from previous experiments in the Omega laser facility and embedded the plastic foils inside a pulsed magnetic field generator known as MyFEDs. So this generates a magnetic field with an initial field with characteristic strength of about 80 kilogauss at the target center here. It's generated by this large electromagnets, and it has the following magnetic fields geometry. The field lines have the geometry shown here. This source of magnetic energy has about, well, the magnetic energy associated with fields of this strength is about 10% of the jet kinetic energy. And so its dynamical significance in principle should still be limited, but this is now a seed field that's 8 times larger, or 8 to 10 times larger, I should say. And then we applied exactly the same diagnostics to previous experiments, X-ray imaging, Thomson scattering, and the proton radiography. And so to illustrate the effects of the larger seed fields, we performed a MyFEDs versus no MyFEDs comparison with all the diagnostics. I'm going to focus specifically on the X-ray imaging and PRAD comparisons in the next few slides. So again, just to show you what these images look like in the no MyFEDs case before making the comparison. So we're now doing, this is X-ray imaging, but it's out at a slight angle to the interaction field, into the interaction region plasma, I should say. Same resolution as before, still looking at soft X-rays. And so this initial images, we adjusted the sensitivity of the camera, and we can now, at this pre-collision stage, see the passage of the plasma jets through the grids, and actually see some evidence that the jets are already beginning to break up and become turbulent. Then subsequent to the collision of the two jets, 27 nanoseconds, we begin to see the formation of the interaction region plasma again, and then its subsequent development. And actually the nice thing about doing it from a slight angle, as you can see here, is you actually get a better view of the whole plasma, and you can see the turbulent fluctuations a bit more clearly, and the whole region then expands to this very large region by late times. So those are the no MyFEDs images. Now let's do a comparison of the MyFEDs and no MyFEDs. At the pre-collision stage, we see that the initial plasma jets protruding from the grids are much more extended and collimated when we included this the MyFEDs. And then the interaction region with the MyFEDs on had a greater transverse extent and restriction than at the equivalent times with no MyFEDs. However, the fluctuations themselves and the X-ray emissivity seem broadly similar qualitatively with and without the MyFEDs. And indeed, we can actually be a bit more quantitative about this. I'm not going to discuss this right now, but we can firm up these conclusions and see that these kind of qualitative observations do indeed hold quantitatively. And it turns out that all of these features, the extension, the increased extension of the jets, and the increased expansion of the MyFEDs, seeming increased expansion of the MyFEDs on case, can actually be attributed to about a 5 to 10% increase in the jet velocity due to the collimating effect of the MyFEDs on the initial jets. But otherwise, and this is seen in the fact that the fluctuations and the emissivity are broadly similar with and without the MyFEDs, and also from our Thomson scattering measurements, which I'm not showing here, we found that the MyFEDs generally had a pretty limited effect on the physical state of the plasma and its turbulence. So that's this basically saying with the MyFEDs, the dynamics is not very different. And what does the proton radiography say? So again, I'm going to start off by showing the no MyFEDs images from the angle, which in this case is now side-on directly perpendicularly through the interaction region plasma. So we see at the point of collision, the early images have these very weak features in terms of flux, and the path integrated fields associated with them are quite small. However, and again after collision, we then see these very large amplitudes in homogeneities appearing in the radiographs, and then the associated path integrated magnetic fields have this stochastic structure with a characteristic root mean square value of about 100 kilogauss. So now making the no MIFEDs top row with a MIFEDs bottom row comparison, first starting off with the images at collision, we see that the MIFEDs images have this very enhanced variation compared to the no MIFEDs case. And this is actually consistent with there being a much larger seed magnetic field in the interaction region with actually, it turns out, a comparable value to the what should be there in the case when there's no plasma at all. If we then move over an indeterminate time later and look at the post-collision structure of these images, there is this significant structure away from the central interaction region plasma, but then we also still see these order unity fluctuations. And then if we then back out, again, the path integrated magnetic field structures, we find that there's actually qualitatively and quantitatively very little difference between these two. In fact, statistically, we find if we do the same things I mentioned for an earlier omega experiment and work back out a power spectrum of these fields, we see that within the uncertainty of the measurement, they're basically identical. And so what we conclude from this is the field amplitude post-amplification is independent of the initial seed field value. And this therefore confirms that, that we're hitting some type of ceiling, and that therefore this would seem to imply that a very strong candidate for that ceiling is the fact these fields are becoming dynamically significant. Now I'm aware I'm basically out of time here, but I just thought I'd finish by summarizing the results from all of the turbulent dynamo experiments and kind of saying where we are and where we're going to try to go next. So it's not strictly a fair comparison because I haven't controlled for all the parameters, but it's quite interesting, I think, at this stage to plot for all our colliding laser plasma jet experiments, do phase-space plots of magnetic Reynolds number versus the amplification factor, and also phase-space plots of the magnetic field, magnetic Reynolds number versus the magnetic kinetic energy ratio. So these are the plots here on the left and right, respectively. And I think you'll agree in both cases, there does seem to be evidence of a trend emerging. In particular, the amplification factors seem to be much larger, significantly larger at larger magnetic Reynolds numbers. And in addition, the obtained values of the magnetic kinetic energy ratios do seem to also be significantly larger at larger magnetic Reynolds numbers. However, as you can see, these plots are still quite sparse. And so I think you would agree that more data is needed before we can come to any firm conclusions on this. And this is currently what we're in the middle of engaging in this process. So we have 2 omega shot days already looking at this, trying to really fill out this plot, with the PI being Charlotte Palmer at Queen's University Belfast. And then we have another 4 shot days in the pipeline, that's by the end of which we really should have be able to complete both of these plots in much more detail and control for parameters as well. I should also mention that recently there's another group that started doing some laser plasma dynamo experiments with a very different setup. This is led by Huili and Kirk Flippo at Lannel. And this is, I think, actually quite a positive development, because if they can see or find or actually even disagree with what we see at in a different geometry, that would be quite an interesting result and should hopefully build confidence the conclusions that confidence or not, I should say, in the conclusions that we have got here. So I think I'd like to come to a conclusion now. I think my time is up. But I'd just like to conclude by saying that these recent experiments on Vulcan, the Omega Laser Facility, and the LMJ and National Mission Facility all have demonstrated the action of the fluctuation dynamo in various different types of turbulent plasma. We've looked at the low Prandtl number regime, the order unity Prandtl number regime, and these are both collisional plasmas, and in that case, we saw very rapid amplification of driving scale magnetic fields. We've also looked at this pre-dynamo amplification regime by supersonic plasma turbulence, and then finally this quite interesting kind of in principle large magnetic Prandtl number, but because we're marginally collisional, we're not quite sure as to exactly how to interpret this, but nonetheless some type of large Prandtl number marginally collisional dynamo. And I think what I hope you will have got from this, and I'd be delighted to talk about this in a bit more detail, is that I feel that laser plasma dynamo experiments really do represent a significant opportunity for improving our understanding of magnetic field application in astrophysical environments. Petros Safarakos wrote a nice white paper on this last year. And then we can explore various things and access new regimes that we couldn't do previously with these sorts of experiments. And in addition, there were actually, and I haven't had time to talk about them today, but there were numerous possible uses of these efficiently generated dynamically significant stochastic fields for other types of laboratory astrophysics experiments. So with that, I'd like to close, and I'd be delighted to take any questions.
Right, thank you very much, Archie, for a very interesting talk.
Thank you.
Questions? Please just raise your hand in the usual manner. Xavier, you seem to be top of the list. Off you go.
Thanks. Well, it was a very nice talk. Thank you. I think you mentioned at some point that the seed field is probably provided by a Biermann battery effect. So
Yes.
I was wondering whether this could be diagnosed by measuring separately the pressure and the density to see whether there is a misalignment or not.
That's a good question. So, so I should say that in difference, not in our precise geometry, but in effectively the geometries of just a single foil being irradiated, there have been quite detailed measurements of Biermann generated fields, where, for example, people have simultaneously measured the magnetic fields and also done exactly what you suggested, using Thomson scattering to try to measure pressure and density gradients. We haven't been able to do those specific measurements in our setup so far, but I think it's a good idea, and we probably could do those sorts of measurements, but we'd have to move our Thomson scattering geometry, but it should in principle be possible. And you'll be right, it's very interesting to see the evolution of the initial Biermann seed fields as they move towards the interaction region plasma. One thing I should make clear, actually, which I'm not sure I quite mentioned as well as clearly as I should have done, is that the Biermann battery mechanism is not, we don't actually think it's acting at the point when in the jets as they move and then collide. What's happened is that it has been generated by the misaligned gradients at the foils, and then basically that field is then just moves with the plasma and is advected into the interaction region. So there's no, in fact, the reason this matters is that the initial Biermann fields that are generated, the laser spots, are actually very significant, have a much larger magnetic field strength, anything up to a megagauss of strength. But basically, in the time that they're advected and the whole plasma expands, and there's the field strengths are attained decay very significantly. And so if the Biermann mechanism was still operating and maintaining this very large field strength, we wouldn't end up with the small seed field that we'd need to actually see any dynamo action. But no, it's an interesting suggestion. It'd be nice to see the evolution of those, the Biermann the seed fields a bit more clearly than we've managed to so far.
Okay, thank you. Well, if the chairperson allows me, I have a related question, very naive. Thank you, David. Is it really impossible that the seed field is provided by an instability like the Weibel instability?
That's a very good point, and so a good question. So as I'm sure some of you are familiar, there have been also done at Omega recently some very interesting, I guess in the last 5 to 10 years, interesting experiments showing the emergence of the Weibel instability between counter streaming jets. There are a few, the reason we think the Weibel instability is not playing a particularly significant role in these experiments compared to those ones is those other experiments have typically used front side blow of plasmas, and you have much faster plasma flow velocities in the jets of around 1,000 to 1,500 kilometers a second. And the interjet, I should say, collisional mean free path is very strongly sensitive to those initial jet velocities and decreases very significantly if you're going to slower velocities. So in our cases, where the jet velocities are only 200 kilometers a second, maybe 250 kilometers a second. So that being the case, basically the collision, as in our experiments, when the jets collide, the transition from a kind of counter-propagating collisionless phase to a collisional phase is much, much more rapid than it is seen in the case of those Weibel experiments, for example, by Wilcox or Huntington. So whilst we've seen some evidence that maybe at very, very early times, the initial interaction could have some type of collisionist or Weibel type physics going on, but I think basically very quickly that those sorts of instabilities we think are collisionally damped, and then Weibel is no longer playing a role, basically.
I see. Well, thank you very much again. Nice talk.
Pat?
Hey, thank you. Interesting talk. We in the course of the summer and many times have heard quite opposite statements on the effect of shear on the small scale dynamo, right, as a suppressing mechanism. And here it seems to be a booster. Could you elaborate on that? I mean, the noticeable difference is, of course, the presence of the Kelvin-Helmholtz in your story, which did not appear in other stories we heard. But I mean, what's going on there?
That's a very good question. Let me go back to the slide I had about this. In effect, so I talked about these strong shears. The first difference, I think, from the other work you were mentioning with these shears is that the shear I'm talking about here is not really very scale separated. Almost there. So here we go. So basically, the scale on which you get these shear flows is seems to be related to basically the grid spacing. So about 400 microns, and it's actually comparable to what we think is in the other directions is the characteristic outer scale of the turbulence as well. So what you're not looking at here is like some very large scale shear interacting with some small scale turbulence. It's these. Another way of thinking about it is basically to say you have a turbulent field, but it's not. The one component of it is quite maybe 2 to 3 times larger than the other 2 random components initially, and that's just due to the geometry of the experiment. So I think that's potentially a source of one difference. Another difference, which I didn't mention, which is why, our analysis of the fascinations indicated that the shear flows were probably the dominant effect in resulting in this increased growth rate. Another thing that is going on here as well, which I didn't mention, is that as time passes, you have the initial collision, but you continue to have high density material flow from the foils flowing into the interaction region, plasma. And so the density of that plasma is actually increasing as well. And so you probably also have some compressional amplification. So that factor as well probably is helping magnetic field amplification. It's not that second factor is not a huge factor because the density maybe increases from the point at which the interaction region forms to maybe at a later time it maybe increases by a factor of 2, but that will help increase the speed of the growth somewhat. But yeah, so I think in terms of your question, I think the shears in this case are not kind of like a large scale shear with small scale turbulence. We're talking about shears on the same scale basically.
But I mean, let me play devil's advocate. Is it really fair to call it a shear, or is it in some sense a way of injecting energy in at small scale?
That's fair. I suppose the reason we ended up describing it as a shear flow was because I didn't show it here unfortunately. If you take a line out along here, these little sheets do look something like what you might expect in one of these Kelvin-Helmholtz shearing instability flows you have. So that's why to me it invoked a shear. But I can see your point that maybe within the framework of like the discussion of this topic in dynamo theory, maybe invoking a shear here is not helpful because as you say, maybe it's better conceptualized as you say, just that we're not, rather than injecting as we do as done in periodic box simulations, the dynamo isotropically, you're effectively injecting energy in more in one direction and then in the others. So it's like an
injection.
Yeah, exactly. No, that's a fair point. Maybe that would be a more helpful way to think about it. It would be quite interesting on that note, actually, if one were to do a periodic box simulation dynamo, but with anisotropic forcing of the sort maybe we see here, to see whether you end up with how that affects dynamo growth rates, for example. That's a really interesting idea. I hadn't thought of that.
Well, since our chair is being lenient, I'm going to get in another one. Very basic. I actually have 3, but I'll wait for the third one. Very basic question. What's happening? You talk about dynamical significance of the field, which that's a very good point. What's the saturation mechanism for the small scale dynamo in these experiments?
In these experiments, so that's a very good question. So it's quite, from the experimental data itself, we found it relatively challenging to actually get at that question, because obviously we're measuring everything kind of indirectly. I think probably the best way to approach that would be to, well, one of the interesting ways to approach that would be to look at what's going on in the flash simulations of this. What we find is that in the flash simulations, at about, well, so the most basic analysis you can do is, for example, in the flash simulations locally, you can calculate, okay, how is the magnetic field's energy compares them to the kinetic energy in particular locations. And what we do see, if you do kind of probability density functions in the flash simulations, that there are localized regions where those energies actually are comparable. And so presumably there's some dynamical back reaction. But in terms of the actual mechanism, that's not something I've looked at particularly. It would be interesting to think as to whether, given there are, for example, that is an interesting question, because given, for example, the flow pattern itself is quite different. It's not obvious, as you kind of, I think maybe alluding to, it's not obvious that the saturation mechanism would actually necessarily be the same. So that's a good point. I haven't looked into it in detail, and it would be something interesting to explore.
Right. All right, thank you. I'll shut up for a while, David, but I'll get back in line.
Oh, okay. Thanks. Guillaume, you're next in line.
Sorry, I thought it was earlier. Okay, thank you very much. Very nice talk. I'm looking at the, well, if I remember correctly, the VKS experiment, they were having problems with their soft iron impellers. Could you be more with such similar problems where you could actually be amplifying from your grids or from whatever, and your field by an alpha effect, and could it not be merely turbulence that's doing the job? Could you disentangle both effects? Are you sure that you don't have any such problems?
That's a good question. So the grids are actually made of plastic. We've not had that's an interesting thought. I not considered the possibility that they the grid, given that case, that whether there'll be any magnetization effects similar to what went on with the VKS experiments. Actually, if anything, what we haven't shown it here, but we did do some. So the way that this model is modeled in the flash simulations, basically the grids is treated as entirely rigid and just basically providing a boundary to the simulation domain. But you can, in principle, also do simulations when you regard them as like initially a very cold but high density fluid, and then see whether, for example, the grids, how they melt. And we actually have some experimental evidence that the new grid design at late times has effectively broken down to a certain extent. And what's interesting is that those, rather than actually helping magnetic field amplification, or it seems to hinder it, because basically the mixing of very cold material from the grids into the jets actually significantly increases the resistivity in the jets. And so any magnetic fields, the Biermann fields that are kind of coming from the laser spots, actually decay more rapidly if the grids are breaking. But no, I didn't, given, the grids are plastic rather than iron, we're not aware of them playing a significant role. I suppose maybe one thing that one could do would be, and this is something we haven't done yet, but would be interesting to try, would be, for example, making the geometry of the target larger, maybe making the interaction region plasma further away from the grids, and maybe that could have an effect. And we could use that maybe to see whether the grids are playing any role. But so I don't think, that we have similar problems. I suppose one of the main things about this setup, which I do quite like, is that in principle you end up with the plasma that you have doesn't have any solid boundaries it's interacting with, because of the geometry of the setup of this plasma itself. The interaction medium plasma, I should say. Unlike, and that's something that's kind of hard to slightly get away from with liquid metal experiments. I mean, of course, there are other advantages to the liquid metal experiments, which is that this plasma, having formed, then expands and decays, and you can't it's hard to kind of drive a turbulent flow like this in a steady way as you can in a liquid metal. So some advantages, these experiments, some disadvantages.
I have a second one then.
Yeah.
When you were mentioning the discrepancies between what you measure and the flash computations, you mentioned that it could be related to additional physics, not in NHD, or differences in spectrum, differences in dissipation mechanisms, a lot of subtle effects. But on the other hand, you hardly know the geometry itself of the flow, right? It's quite difficult to infer that, because you're either very well localized or very and have a full time resolution, or the contrary. So how can you compare apples to apples? And since you're showing that precise figure, it seems that quite often you seem to have discrepancies between your line integrated field and your the proton radiography, which probably is a measure of the string function, and you'd expect that both should overlap. So do you understand those discrepancies?
And so I slightly lost you for the last part of that question. I couldn't hear what you said.
Okay, sorry. I was saying that you seem to have in a few of the pictures that you were showing discrepancies between your field integrated measurement and the proton radiography, which is probably more a measure of the string function, right? And you would expect both to match quite closely. So, well, do you understand those discrepancies? And I guess the connection with the discrepancy between your computer simulation and your results is, well, you don't really know the flow geometry, and how does that impact what you can say or cannot say? Because that's probably a very important part of the story as well.
I mean, yeah, that's a really good question. So in principle, the techniques that take us from, say, so the purest thing we collect is this experimental data shown here at these 2 times. The techniques that take us from this, the proton radiography to the path integrated field, which, as you say, is basically a measure of a kind of path integrated potential function, are, well, they're made under certain assumptions, but usually for radiography setup, these assumptions are pretty good. So in principle, the experimental images should be consistent with the path integrated fields. But in terms of the relationship between these two, it's, to be honest with me, it remains one of the biggest puzzles we're trying to understand, because as you can, I think probably the clearest way to see it is just to look at the simulated images from the flash compared to the experimental data. There seem to be features, for example, these kind of structures extending from the grids that don't seem to be evident in the experimental data, which maybe suggests that there's something going on with that interaction that we're not capturing correctly at the moment with the flash simulations. And so, I mean, as I mentioned, we've tried to make the geometry as realistic as possible with the flash simulations, as they're including the grids, getting the laser deposition the same as in the experiments, and the exact kind of parameters. But one of the issues we face is actually the simulations themselves, because they have to be 3D and they include all these effects, end up being very expensive. So you inevitably having to make some approximations along the way or not include certain effects. And it seems to be the case that there's some effect that we're not including here. Maybe it could, these I should say, for example, these experiments, this simulation didn't had just a fixed grid. And so it'd be interesting, for example, to compare this if you include a grid that could evolve as well, whether that might help resolve some of these issues. But yeah, so in terms of what I mentioned, these possible explanations for why the flash simulations aren't getting this right, what would be interesting to see is, well, and actually this is a kind of a medium-term plan we have to addressing this, is basically, because the simulations are very expensive, and because you're having to introduce this geometry, one thing we could maybe look at is, for example, actually do periodic box simulations and then see whether introducing these different bits of physics makes a difference. So, for example, do periodic box simulations with Flash, but includes, so they've now actually introduced into Flash some of these additional terms of an Ohm's law, and so see whether that makes a difference. Or you could, for example, with a periodic box simulation, which again is cheaper, you could introduce explicit viscosity and then see whether that makes a difference. And then you can kind of basically hone in on these different factors and work out what seems to matter and what doesn't. And then if you, for example, you find that one of these kind of simpler periodic box simulations does indeed result in fields being on a larger scale, that then is suggested that could be the important effect. But I suppose at the moment, what the trouble with the simulations we've got is that in principle, all of these could be acting, and it's hard to just rerun the simulation as is, but including these effects, because it just gets very expensive at that point. And does that answer your question?
Yeah, partly, but on that one, for instance, looking at the first row, the first line, sorry.
Yeah.
Would you, maybe I misunderstood, but would you not be expecting that both geometries of the structure in the experimental data should overlap? That you should have a concentration of the field where you have a concentration of the stream function or the flow, or maybe you're not seeing the flow as well.
Oh, I understand what you're saying. Okay. So maybe I shouldn't say. So it turns out that in terms of what you see in the actual images here, given the point projection geometry, what you end up. This is these maps can be interpreted in terms of structures. This is it's something along the lines of it's the path integrated parallel component of the currents. So I say parallel, I mean parallel to the direction of the proton beam. So that's what this image is really sensitive to. If you, for example, and so basically if you take these path integrated fields shown here, calculates this is the two components perpendicular to the direction of the proton beam, and then calculate the curl of those, and then you end up, that gives you the parallel components, and then compare it to these images. Then there's basically a great similarity. So where there's like a concentration of photons here, that's where you'll have a high currents, and in one direction. I can't remember off the top of my head whether a high proton current corresponds to a current anti-parallel or parallel, and whether the voids are the other way around. But sorry, so I now understand. So the fact you have structures in different locations here, so where there's strong fields here and not the locations we get high currents, is to do with the fact that these images are not you're extrapolating the path integrated field. What you're basically looking at here is the path integrated components of the parallel currents. So that's what correlates here, if that makes sense. So yeah.
Thank you very much.
Oscar.
Hi. You also had some power spectrum data from NIF, if I understand correctly, and that seemed to go down as we went to large scale. Somewhat. Like if we look at it after this picture, I think it's. So did you? The question is, did you compare these two in detail, like looking at boundary conditions or box size and things like that, which would explain? Yeah, I think you just went through. So this was a power spectrum.
Okay, turbulent spectrum. Okay, cool.
So is that meaningful?
So the comparison, that's a good question. So I think you can meaningfully make a comparison, and you can see that both. So the spectrum deduced in this case from the NIF data itself directly is the blue here, and actually this red spectrum is from the flash simulated data. So you can see. Yeah.
That here you have an agreement. So why? What is the difference? Is the box bigger? Is
I understand. Sorry, I should explain a bit more carefully. So this is the power spectrum of inferred power spectrum from the emission fluctuations. So what I should be clear. So we found Flash actually seems to model the hydrodynamics pretty well, and so we consistently find that the spectra of deduced from these X-ray images
of fluctuations.
Yeah. So the spectrum of fluctuations in both cases we find to be consistent between Flash and
I see.
And the experiment, but it's the magnetic spectrum.
I see.
Seem to be different.
But it's also different for the NIF case if you look at it, or did you look at it?
So that unfortunately we just don't know, to be honest with you, because so point I made basically about the fields being are so strong on NIF that the protons are kind of scattered all over the place means that we actually, so for the diagnostic to work and be able to back out the magnetic energy spectrum from those path integrated field maps I showed you, you can only deduce those maps in the first place if the beam doesn't self-intersect before it reaches the detector. And what we find for the NIF experiments is that the gradients and the deflections are so large that the beam is kind of completely self-intersecting with itself and being scattered all over the place before it reaches the detector. So basically, we've kind of lost information with this. We've lost spectral information. We don't know where the protons have come through from. So we don't have a spectral measurement of the magnetic field for NIF at the moment. And this is something we really like because it would be wonderful to be able to actually resolve it. So we're currently working on new alternative approaches for trying to characterize the spectrum, just because this particular diagnostic just won't be able to do that.
All right, thanks.
Okay, maybe I can ask a question before we go back to Pat. So if you're doing kind of classical dynamo problem, you've got a well-defined magnetic Reynolds number because the induction equation just has a del squared B. But in yours, presumably, it's way more complicated than that. I mean, that comes from the simplest Ohm's law you can think of, whereas yours is way more. So what do you mean by what is a magnetic Reynolds number in your setup?
Yeah, so that's a very good question. And to be honest with you, I think you could probably regard as like a fundamental limitation in some sense, having me being optimistic about this toolkit as a limitation of these experiments is, as you say, the complicated evolution. So one can, let me start by how I am when I can't report these numbers, how I'm calculating them. So we measure directly by the Thomson scattering the turbulent velocity in the system's RMS turbulent velocity. We measure a characteristic outer scale of the turbulence, and we typically find that that's consistent with the grid scaling, a grid periodicity, so about 400 microns in this case. And then take the resistivity. For a collisional 2-ion species 1 electron species plasma, one can calculate using collisional transport theory what you think the resistivity should be from that in terms of the macroscopic, in terms of the temperature and the density. And so we can then infer a resistivity, and then using those two parameters calculate a magnetic Reynolds number. Now, you're right, this is not, in some sense, that quantity will evolve as all the parameters of the system change over time. And so for that reason, I can give a value and then compare with periodic box simulation, for example, but there is a question to ask, well, how reasonable is that comparison? I mean, I think the way we looked at it is that was probably, it seemed to be us the most reasonable way to try to infer a magnetic Reynolds number in these sorts of systems. But actually, it's something that this experiment illustrates here, and actually, so I'm not showing it here. So it turns out that after the plasma interaction region forms, I said the density goes up, so that affects the fluid Reynolds number. But then also, it turns out at later times, the temperature drops off quite significantly. Although as I said, it doesn't really show up as well as it might do in our Thomson scattering data. And so therefore, in principle, this is the inferred value of the turbulent magnetic Reynolds number initially for this kind of 4 nanosecond interval after the collision, but then by later times, it's going to be quite a different number. I suppose, it's a good question. Maybe this is I said, maybe you could regard this as a fundamental limitation of these sort of experiments, because there is this complicated evolution. We have actually, we are currently working on a development of this platform, which basically via laser heating keeps the plasma at a much more consistent temperature. So at least if you're rather than having this kind of time evolution of the parameters, you should end up with a system with an approximately constant magnetic Reynolds number as defined in this way for, say, a 10 nanosecond interval. And then maybe that becomes something that's a slightly closer comparison to a well-defined kind of RM, for example, in a periodic box MHD simulation.
Okay, so but in the flash simulations, is there a well-defined RM? I mean, is there a uniquely defined RM, or are they complicated as well? So in the flash simulations, the way they do resistivity is
and I should say I haven't looked into detail at this, but my understanding is what they're doing is they have explicit resistivity, and what they're doing is that the resistivity they're using is macroscopically parameter dependent in the same way as this quantity, as the quantity I gave here. So basically, they're using Spitzer resistivity for that. So that therefore means that, of course, over the whole simulation domain, that resistivity is changing a lot. What I've not, to be honest with you, and this is something how this then works if, for example, in some regions you have a very high resistivity, in other regions you have a lower resistivity, how that then works is, I guess, it seems to me quite subtle. And so I don't, to be honest, have a full understanding of that. But so that's, I said, in principle, for flash simulations, they do have explicit resistivity in that, but it's in that sense. And so again, it's not kind of a constant resistivity in the nice way that you would have in a periodic box simulation. I think Flash does actually have the capability to use a constant resistivity, but for these simulations, this kind of macroscopically varying resistivity was used.
Right. Okay. Whilst we're on magnetic Reynolds numbers, what is the ohmic time of yours in nanoseconds? Let's say if RM is 4,000. How long are you running these simulations, these experiments?
About another very astute question. So I'm not. I'm trying to think. It's on the order of tens of nanoseconds. So it's basically the ohmic time is probably going to be longer than it's of the order of like 15, 20 nanoseconds. I would think maybe it could even be slightly longer than that. So that is again another limitation. It's very hard to create like a nice steady state dynamo that's persisting up to, say, an ohmic time in these systems, because the whole plasma then expands and kind of decays away in a short period of time. So one thing when looking at these experiments, one mustn't come to the conclusion, it's not like we've taken a periodic box and run it to steady states and then reach some nice saturated value. What effectively we're doing, we're having a very short interval of which you're getting significant magnetic field amplification, and then that's all you get to see in these experiments. Mm-hmm. This could be a problem because, of course, in principle, there are some, and as you'll know, there are some systems where you can get kind of transient amplification of magnetic fields if you aren't running for a very long time. And so it's a source of some concern. So this is why going forward, I think rather than I think probably more helpful use of these experiments, rather than, for example, trying to really kind of carefully say that they're like let's put this. I suppose what I'm saying is that I think what you could maybe use these experiments more for than kind of a direct comparison with periodic box simulations is, for example, trying to identify parameter trends. So, for example, that last plot I showed you showing, for example, how does the degree of amplification we see the experiments vary with magnetic Reynolds number when you've done a proper control? Because if we can show this in these sorts of systems, for example, you do get significantly more amplification and it occurs in a kind of over quite a sharp interval of magnetic Reynolds numbers, that would, for hypothetical state, that would be quite an interesting state of kind of conclusion to come to, even though these systems are not really, the sort of experiments are not proper proxies for like a well-defined periodic box MHD simulation. In short, so going back to the original question here, the ohmic times of these experiments are quite long, and we don't manage to keep the experiment going for the full length of time.
Right. Okay. I have a brief comment on Pat's comment. I mean, anisotropic injection. I mean, if you push that to the limit, then you will kill the dynamo, of course.
Yeah.
I mean, if you favor one direction rather than the other.
Yeah.
So it's I mean, fast dynamos, fluctuation dynamos that really want exponential stretching, don't they? It's not.
Yeah.
It's not clear that you do that by favoring one direction rather than the other, or even a shear flow would not do that. So no. That's kind of interesting as to why you feel that you're getting a faster growth rate.
No, so that's a good point. I mean, again, I suppose what I'm saying, we're not looking at it's a little bit of a mess in a way, because it's not an asymptotic state. We're not like talking about these shear flows being 10 times or 100 times the magnitude of the turbulent motions. We're talking kind of maybe a fact these shear flows are maybe the Z component of the flow is maybe corresponds to kind of 60% or 70% of the energy in these flows. So it's kind of, it's not really an asymptotic state. And so it's not, I suppose it's a really interesting question to see if that, in that sort of system, and this probably would be better explored in a protocol simulation with some type of anisotropic forcing, whether that sort of situation, whether you kind of, because as you say, that if you go to the fully anisotropic case, dynamo shouldn't work. What happens if you kind of move towards that case? Is there like a regime where you get faster amplification? I'm not sure. That's a really interesting question.
Okay, thank you. I've had plenty of say. Back to you, Pat.
All right. Well, we're having fun here. So this is more of a request than a question, but it comes with a follow-on too. Can you give us a little bit of a soundbite? I know it's running on the issue of the transport in stochastic magnetic fields.
The application.
Yeah, this is extremely interesting point that you didn't really get to in your talk. So,
well, I actually do have some backup slides on that. So let me.
What I thought.
Sorry, not too many slides to go through. Annoyingly, so this other application, which is quite interesting, as I put first. Okay. Yeah, so this is this was work. So this was led by Laura Chen. So it's quite a particular experiment. So what with this platform what we did with this? So we used a modified version of the first Omega platform. So we then, again, using a proton beam created with a D3 helium capsule, which we kind of collimated with a pinhole, we basically measured the diffusion of these high energy protons through the intermittent fields generated in this plasma at different times. And by different times, this basically allows you to sample different widths of the path length. So for example, what we do here is, this is the setup. We then, this is a comparison of what one of these pinhole images look like if there's no plasma versus with a plasma. And you can see there's significant scattering. And so this lateral dispersion of the protons in this setup can then be related to a velocity deflection at different times. And so this is, we look at both the 15 MeV and diffusion of 15 MeV and 3 MeV protons in this case, and then compare that to what the flash simulations have got. And then from this, we infer a spatial diffusion coefficient. So this is the inferred spatial diffusion coefficient. So here, again, flash is the green points in the experimental data is the error bars points here. And within the uncertainties of what we see, what we find is that this coefficient is basically constant for these different lengths over maybe a factor of 3. And so this, in this particular case, seems to confirm that the diffusion of the beam was consistent with just normal Markovian diffusion. And this is what basically, I suppose, from my perspective, the most interesting aspects of this result is, firstly, that these fields, and I didn't show it here, unfortunately, but we have evidence that they're pretty intermittent. If you can actually, where you can look at this, if you look at the PDF of the path integrated magnetic fields that we recovered, it's a non-Gaussian distribution. And if the path integrated field is non-Gaussian, then the field itself must certainly be non-Gaussian. But nonetheless, you still seem to have this diffusion coefficient that is scaling exactly as you would have just assuming Markovian diffusion. So that's what was shown in this particular experiment. It would be nice in some ways to look at, because this is a regime basically where your particles are, the regime we're accessing here is the regime where the particles are traveling, I suppose I guess it's equivalent, it's at high rigidity, so they're traveling, their deflection angles are relatively small. They're not like gyro orbiting inside the plasma. They just, so it would be nice, for example, maybe to try to look at this sort of high energy particle transport, but in a different parameter regime, which is perhaps more relevant to say lower energy cosmic rays, because in some sense, this regime is only, I guess, is probably most relevant to something like ultra high energy cosmic rays. But then again, by the time they're ultra high energy cosmic rays, they might have, there's some other physics that's probably going on there as well, which might not be relevant to this. that's what we've done so far with this. It's still be nice to try to develop this a bit further.
You haven't got to the point of trying to test some of the classical wisdom on transport and stochastic fields then? You know,
Not yet. I mean, understanding charged particle diffusion and also fundamentally acceleration as well is something that I know, for example, Gianluca is very interested in. Is a case of getting it to work, because so one of the main constraints at the moment we have is, for example, the energy of the protons, and typically the sort of fields we generate, even on NIF with mega-Gauss fields, an MEV proton will usually, whilst it will be scattered quite a bit, it's the amount of acceleration you're getting from that sort of proton is not that large. So basically we need to try to get to higher fields, even higher fields than we do on NIF, maybe with a different geometry, before we can start to probe, say, acceleration. But yeah, it's something there's definitely active interest in. It's just a case of making it feasible in the laboratory with these sort of platforms.
Indeed, indeed. Is there any hope down the road of trying to get some insight? I mean, you had in this discussion, you have this, which right now, and we, you know, talking about instability, familiar animals in the instability zoo along the way. Getting some insight into the effect of, or the physics of the saturation of these instabilities, particularly due to, you know, particle scattering and so forth, right? Whereas there is, of course, a whole school of thought on things like that very rarely gets tested except in computer simulations. And I just, you know, it's sort of an obvious direction for you.
Yeah, no, you're absolutely right. You've read my mind. I'd love to do experiments on that sort of thing. I think, so probably the first sort of, in terms of the saturation of kinetic instabilities you could look at testing is actually, there's quite a lot of, because it's much easier with these platforms to get magnetized electrons. So a lot of the time, it seems to me that some of the instabilities you mentioned on with these dynamos, this relevance dynamo, involve, you basically need to have magnetized electrons before they start to operate. Things like the Whistler heat flux instability. There's been a lot of work on that in the astrophysical context recently. And so we now know that we can access that regime on NIF and get very strongly magnetized electrons. And so, yes, I think with a suitable modification to this sort of platform, you could start to look at that. My own instinct on this is that probably trying to do this in a turbulent, it might be sensible to try to do this in a slightly simpler setup. So one where you still have a strong magnetic field, but maybe it's not, the large scale field itself isn't turbulent. If you, for example, could create a plasma which is magnetized that had a temperature gradient in it, and take the heat flux example and then investigate the evolution of the kinetic instability with that, I think that's feasible to do in the lab and would be easier to interpret. Actually, because it's relevant, let me go back to another application I mentioned, which is kind of indirectly relevant to this. So I mentioned there's this very recent paper out, first author Jenna Meinecker, looking at suppression of heat conduction. So that's one of the kind of microphysical effects that have been people have attributed to these instabilities causing. So what Jenna did per this NIF experiments was basically she modified our X-ray framing camera diagnostic such that she obtained images with two different filter types. So in her case, she was using the polyamide filter and a vanadium filter. And then basically, my iPad has stopped working. Okay, there we go. So then taking these two filters, you can take a ratio of the measured intensity for these two values. And actually, with the setup, she designs this ratio of the two detected filters is not very sensitive to density, but it is sensitive to temperature. So you can calculate these kind of ratio curves, and we're always in a regime in this experiment where we're above the turnover of this curves, and so the given value of the ratio is associated with a given value of the electron temperature. And so then this allows you to infer some type of temperature map. And what was very interesting is that, so we did use this on omega and NIF. So for the omega experiments, recent ones, we found very uniform temperature profiles. But on NIF, we found these incredibly structured ones. The flash simulations of these experiments seem to reproduce the omega data very well, just using Spitzer conductivity. But if you do the same thing with NIF, Spitzer conductivity simulations don't give anything like the right answer at all. And you only come close if you just basically turn off explicit resistivity, explicit conductivity in these experiments. And so this is, and the reason for the difference, the omega experiments, as I mentioned, are only marginally magnetized even post-dynamo amplification. But on the NIF case, the electrons are very strongly magnetized post-amplification. So these different, basically things like the Whistler heat flux and stability could well be operating in the NIF case. The issue with the NIF case is that there are all sorts of physics that could be going. You've got this complicated stochastic fields. You've got potentially actually these gradients are so large, non-local effects might start to matter. And so I think if you're going to look at these kinetic type instabilities, it would make sense to basically move to a slightly simpler setup, but one that access to similar to parameter regime. But then I completely agree that theory is a really good idea is to do experiments investigating those sorts of kinetic instabilities in the lab. And electron instabilities are the easiest to do in that regard.
Sure. Yeah. All right. Thank you. Yeah.
Okay. Guillaume, did you have another question? Was your hand?
I have a quick one. Yeah. Okay, you showed while answering David the saturation of the energy density with the time after the laser pulse.
Yeah.
And you also discussed the fact that changing the strength of the seed field doesn't seem to change the end result that you get. So is it correct to think that if you were to pulse your laser and to have, with a high frequency blobs of plasma colliding so that you can maintain almost in steady state, if that is possible, your plasma where you can measure a thing, you in fact would not amplify beyond what you already have, your seed fields. And if that is true, does it say something about the validity of your mechanism to explaining astrophysical magnetic field strengths?
I could see. So I just to be clear, and so in terms of the sort of the relevant timescales of this, I maybe should have been clearer. So for most of the experiments I described here, what you typically find is that the pulse length of the lasers, the drive lasers you're using is about 5 or 10 nanoseconds, and then that's typically the evolution time of the plasma wave is then we only actually end up studying the plasma when the laser is completely off. It's usually 15 nanoseconds after is when the collision happens, say on omega. And then we study what goes on for probably another 15 nanoseconds after the collision. I'm just trying to get best to answer your question. It would be interesting. I don't know in practice how easy it would be to implement your suggestion, just because there's kind of a limit of how long you can drive on and off these sorts of experiments. One thing you can do in terms of making a steady state plasma is, once you have the collision of the two jets, and this is something we're actually trying in a few weeks' time, is in principle, if you have the collision of the two jets, that plasma becomes dense enough that it actually absorbs laser energy quite efficiently. And so in principle, you can then use other laser beams to kind of keep the plasma in a more consistent state, and then hopefully drive it for longer, and keep it in that state for a much longer period than we can do currently. And so that might be a way of kind of ending up with a more consistent plasma. So I'm not sure I've kind of quite answered your question.
I guess I was asking if you were to drive the plasma for a longer period of time, would the field amplification keep being amplified, or do you think you have
Oh, I see what you're
the
saying.
saturation of your field already, given the amount of time that you have at your disposal to measure?
Okay, now sorry, I now understand what you're saying. Sorry, I didn't quite answer what you were saying before. So I think, well, we actually went back and looked quite carefully at what happens in periodic box simulations. So what typically in those seems to happen is that you have a kinematic stage and then you reach the nonlinear stage, but then, at which the magnetic field starts to back react on your plasma. But then there's quite a long stage of this order of several turnover times before you then reach what would be regarded in those simulations as saturated states. And you are having basically the field, the energy is increasing. I think most simulations seem to indicate it increases linearly in that time. Certainly the small scale fluctuation dynamo simulations I'm familiar with, that seems to have been the finding. But so in principle, if that's the case, and if something similar is happening here, then maybe if you could sustain it for longer, you would get marginal increases in, well, say not marginal, but you would get some increase in the magnetic energy if you could sustain it further. As I said, actually, one of the main goals for this upcoming shot day we have is to see whether if you can sustain the plasma in a higher, in its kind of heated state and keep allowing fields to be generated, whether this does allow you to get to higher values of the field strength than we see. As I said, it's quite interesting because there are some circumstances given, as I said, with this final experiment where we had this larger seed field, there are some circumstances, depending on parameters, when you might have, even if that field has become dynamically significant, it should still have time to increase a bit more than the case when there's no seed field and you have to have some growth first. So the fact that these fields were so similar with an error was slightly surprising to us. But in short, I think you should be able to, hopefully with the development of this platform, we should be able to keep this plasma in a heated, turbulent state, and then see whether magnetic field growth does continue to occur for a longer period than we've done currently. Yeah, your suggestion is a very prescient one.
Right. Well, we've gone on for 2 hours, so maybe we should, we've probably questioned Archie enough. Anyway, but thank you, Archie. That was a very interesting talk, and as you can see, one that has generated a lot of interest among the audience as well. So thank you.
Thank you very much, and thank you for the invitation again. I really appreciate it.